Good morning, everybody. Welcome back to Real Analysis. Plan for today is, what did I say, limit axioms? I'm sorry, I'm still in calculus mode. Axioms of the real numbers. We're going to continue our discussion, focusing today on looking at kind of the third and final category of axiom that we're going to have for the real numbers, the one that's the spiciest. As far as office hours go, I've changed them around. I have noticed we're supposed to get like 8 inches of snow today. So I decided so I can avoid having to travel through some treacherous weather this afternoon, I'm canceling my office hours for today, and instead holding an extra hour and a half of office hour tomorrow morning from 10 to 11:30. So so these two office hours are basically getting moved to tomorrow morning. If you're planning to come by today, I apologize. You're welcome to email me with any questions you have, or I'd be happy to meet with you tomorrow sometime to talk about whatever ails you. And as a reminder, homework 1 has been posted on Canvas and is due a week from today in class. Any questions or comments before we get started for today? Why did the yardstick want his parents to stop supporting him financially? It's because the yardstick wanted to stand on his own 3 feet. Okay, and with that, let's go back to talking about the axioms. So on Monday, we said our real number axioms, our axioms for R, are going to be statements about the real numbers that we're not going to give any logical justification for. These are just properties of the real numbers that we're going to assume are true, and then we're going to, in order to be able to use these properties later to prove a bunch of stuff. So first set of axioms we had for the real numbers were the field axioms, which basically said addition, multiplication, subtraction, and division work, quote, nicely, in the sense that we have closure, meaning if you add or multiply any two real numbers, you'll always get a real number back. Identities, and that 0 and 1 are real numbers, such that adding 0 doesn't change anything, and multiplying by 1 doesn't change anything. 0 being the additive identity, 1 being the multiplicative identity. We have additive and multiplicative inverses, meaning if you give me a real number A, I can find something to add to it that'll give me 0, and we'll call that number negative A. And similarly, as long as A is not 0 itself, I can find something to multiply A by in order to get to 1, which we'll call that number 1 over A. Commutativity, you can add or multiply numbers in either order, you'll always get back the same answer. Associativity, A plus B plus C will give you the same thing as A plus B plus C, and ditto for multiplication. Distributive properties tell us that addition and multiplication interact nicely with each other. And then our second set of axioms was the order axioms, which says that we have a subset of the reals, a set of which we'll call positive reals, that's closed under addition and multiplication, meaning if you add or multiply two positive reals together, you'll get back a positive real. And given any real number, either it's going to be a positive real, its negative, its additive inverse will give us a positive real, or that number that we're working with is 0. And that's where we left things off last time. We said that the integers and the natural numbers are going to both fail some field axioms. Specifically, they're both going to fail the field axiom of having multiplicative inverses. The ones I want to look at today, start with, before we move on to the last category of axioms, are the rational numbers, the set of all fractions of integers, and the complex numbers. So first of all, let's look at the complex numbers. Are there any of these field or order axioms that the complex numbers you think are not going to satisfy? You can add or multiply.
Or order axioms?
Order axioms, you claim there's not a set of positive complex numbers that satisfies these properties?
I mean, there would exist a subset of positive complex instead of positive real, right?
Sure, sure. Here we're assuming for C here we're replacing all of our R's with C's.
But since every complex number, I mean,
Don't even close the window on you.
what would it even mean for it to be positive? Because there's i's, maybe like the upper half complex plane, but then there's.
Yeah, both the real and imaginary component are positive real numbers. This is tricky, but you're right. It's going to turn out that the complex numbers are going to fail the order axioms. And the way we can actually show that, Luke, do you have any ideas?
Yes, the real positive is not necessarily closed because if you multiply I times I, it becomes negative.
Yeah. So let's look at I for a second. So let's do a proof, we're going to do a little bit of a proof by contradiction here. If we had a set of positive complex numbers, if I is one of those complex numbers, we know multiplying two complex numbers together, or two positive complex numbers together should give us a positive complex number if the order axioms hold, right? Emily, what do we get if we take I times I? Yeah, so if I is a positive complex number, we get I times I is -1, which would have to be a positive complex number. Okay, that raises some red flags, but doesn't necessarily break anything. We could just have to define positive in a very weird sort of way. But if I, which is a positive complex number, and -1, which we're assuming is a positive complex number, are multiplied together, Lydia, what would that give us? -I, which then, again, by the closure of the positive complex numbers, would have to be a positive complex number. Emily Rose, you have a problem with that?
I mean, that basically just says every complex number has to be a positive complex number, because we defined I as positive complex, and -I is also positive complex, so.
Can that happen? According to our order axioms, can I and -I both be positive complex? Yeah, because it fails the second condition, where we can only have one of these being true. If I is a positive complex number, -I can't also be a positive complex number. So, and contradiction occurs. So what does that tell us? Well, what that tells us is I can't be a positive complex number. Because if I was a positive complex number, it would lead to a logical contradiction occurring. The fact that it's negative would also have to be positive, and that can't happen if I is positive.
By the same argument, you can also say -I can't be a positive complex number, because you just substituted -I for all of those, and it works out the same way.
Yeah, we can say if -I is a positive complex number, on the other hand, well, we get -I, which is positive complex, multiplied by -I, which is a positive complex number. Joel, what do we... Let me start that sentence over. Joel, what would we get if we multiplied -I by -I?
-1, isn't it, still?
Yeah, the two negative signs out in front would cancel out, and we'd just be left with I times I, which is -1. So we get that -1 would have to be a positive complex number. But then we get -I times a positive complex times -1, which is a positive complex number, I asked, what would that give us? Negative I times negative 1.
I.
Yeah, the negatives would cancel out. We just get I times 1 as I. I would be a positive complex. German, what's wrong with this scenario?
We just said that negative I is a positive complex number, now we're saying the inverse, just I is a positive complex number.
Yeah, same logic we had down here. If negative I is a positive complex number, well then I can't be a positive complex number without breaking this condition, that only one of these two conditions can hold. Matthew?
Why do the order axioms matter? Because like, at least in my mind, like, isn't this like all closed if you just look at the just the complex numbers in general? So like, why does it matter if it's like we define it one way as positive versus the other way as negative?
Because hold on to your hats. So this is a contradiction. I'll answer your question in just a second. So if negative I is a complex number, that would imply I is a positive complex number, which can't happen, which then tells us negative I is also not a positive complex number. So let's look at I for a second. I is a complex number. It doesn't satisfy the first property. I is not a positive complex according to our work there. Negative I also isn't a positive complex number because of our work on the right-hand board. Faith, does I equal 0?
I'm gonna say no.
No. I times I squared is negative 1. Does 0 squared equal negative 1? So I is not 0. I is a number for which none of these hold. Therefore, this set of order axioms cannot possibly hold for the complex numbers. Then we get that I is not a positive complex number. Negative I is also not a positive complex number. And I is also non-zero, which will ultimately contradict the order axioms. So, complex numbers are out. They can't satisfy the same axioms as the rest. So Matthew, you asked the question, why do we care about this? Why does it make sense to even try and define a positive set of complex numbers anyways? Why do we care? The reason why we care is something we're ultimately doing is with the 5 sets that we're looking at, the natural numbers, integers, rationals, complex numbers, and the reals. Ultimately, we'd like to be able to talk about some properties of the reals that makes the reals different from any of the others. So far, it's easy to show these two sets have some properties, some interesting mathematical properties not in common with the reals, in that there's field axioms being violated. By showing the complex numbers fail the order axioms, that gives us a way to kind of differentiate the real numbers and how they behave differently from the complex numbers. So we already know that R behaves differently from this set, and that set. So the only question we really have left is how do we distinguish the real numbers from the rational numbers? And that'll kind of give us a way in which the reals behave differently from all the other sets we've defined so far. Does that make sense?
Yeah.
Are there questions thus far? So how about the rational numbers? Do the rational numbers fail the field or order axioms? Well, if we add 2 fractions of integers, are we going to get a fraction of integers? If we multiply 2 fractions of integers, are we going to get a fraction of integers? Okay, so they have closure. 0 and 1 are rational numbers. You can write 0 as 0 over 1. You can write 1 as 1 over 1. So we have identities. We have inverses. If you take the negative or 1 divided by any rational number, you'll still get a rational number. doing commutativity, associativity, distributive properties I'll hold. So for the rational numbers, I would say the field axioms check out. How about our order axioms? Can we define a set of rational numbers that is the positive rational numbers without causing any issues? Faith, what do you think?
I was gonna say yes, but I'm not sure if I can give a reason why.
It's easy to say yes, it's hard to prove why.
Exactly, yeah.
And we're not going to go for a formal proof, but turns out order axioms check out. You can just use the positive rational numbers the way you're used to thinking about positive rational numbers. Ones where a over b is greater than 0 in the usual sense. We'll satisfy all the order axioms for the same reasons that the real numbers are going to satisfy the order axioms. What does that tell us? Is that a and or a just a? I'm just gonna do something amazing with my hand.
I guess that given that, I mean, the real numbers are behaving differently, that it has to be something other than these axioms that differentiate.
Yeah, exactly. But what this tells us is ultimately we need another axiom or another set of axioms in order to give us mathematically different ways in which the rational numbers and the real numbers are going to behave differently from each other. So I'm just going to say we need a new axiom to differentiate Q from R. And so that's ultimately what we're going to be looking for with our third and final axiom of the reals, the spicy one, is a way to sort of say the real numbers are going to satisfy this third axiom, but the rational numbers are not, as a way of differentiating how do the rational numbers behave versus how do the real numbers behave mathematically. So what we have so far, it's enough to make the reals behave differently from N, Z, and C, but it's not enough to make it behave differently from Q. Any questions or comments before we get into our third set of axioms? So, before we start getting into some new axioms, we need to lay some groundwork and do some definitions. So, because the third axiom relates to what it means for a set to be bounded. And what we're going to say is that a set, S in R, is going to be called bounded above if there exists a real number B such that for all elements little s in big S, little s is less than or equal to B. In other words, if a set is bounded above, if we can find a single real number that's greater than or equal to everything in your set. And similarly, we can say that a set S is bounded below if there exists, what do I call it, L, real number L, such that for all elements in your set, S is greater than or equal to L. In other words, your set's bounded below if you can find a real number that's less than everything in your set. So let's look at a few examples of sets of real numbers and see if we can determine whether or not they're bounded above or below. So let's start off by looking at this one. So when I write 110 in these parentheses like this, what do I mean if I'm referring to this as a set of numbers?
numbers between 1 and 10,
including 1 and 10?
not including 1 and 10 unless you use brackets.
Yeah, so we're going to call this the open interval from 1 to 10. Open meaning we don't include the two endpoints, although we'll have more meanings for that word later on in the semester. Which we can write, if we wanted to, as the set of all real numbers x, such that 1 is less than x and x is less than 10. Is this set bounded above? Meaning, can we find a real number that's greater than or equal to every single number in this set? Luke, can you think of a single real number that's greater than or equal to every single real number between 1 and 10?
10.
10 is certainly greater than everything between 1 and 10. Emily Rose, can you think of another one?
12,
Emily, can you think of another one?
13.
Yeah, there's lots of numbers that we can say bound the set S above in this case. You could say by, for instance, 10, or 13, or, I don't know,
100.
999 pi plus 2. That's certainly greater than every element in this open interval from 1 to 10. Lydia, can you think of any numbers that would bound this set below? So in other words, a number that's smaller than, or less than or equal to everything in this set. 1 would certainly do the job. Okay, any others?
-2.
-2. German?
Negative 573.
-573.
-5 pi plus e.
-5 pi plus e. That would certainly also work. There's a lot of numbers, dare I say infinitely many real numbers that can bound this set below. So I would say that this interval open interval from 1 to 10 is both bounded above and it's bounded below. Because you can find real numbers that are greater than everything in this set, you can find real numbers that are less than everything in this set. How about this one? I'm going to skip the second one for now in the packet. How about this set? Set of all numbers of the form n plus 1 over n, where n is a natural number.
Just to clarify, are you still looking at if this is bound above and below in R?
Correct. Yeah. All of these as subsets of the real numbers. There's lots of real numbers in this set, for instance, that are not rational numbers, but we are going to consider those for now. And these are very much, this is very much not a real number. Or not a rational number, excuse me. Definitely is real. All right, Emily Rose, I have a question for you. -5 pi plus e, is that a rational number?
No, I don't think so.
You don't think so?
I don't know how to prove it's not a rational number, other than just I know pi and e are not, so I don't think their sum is.
There's a lot of irrational numbers that sum to something rational, like I added those. Those are two irrational numbers adding to something rational. In truth, is -5 pi plus e a rational number? I don't know. And mathematicians as a whole do not know if that is a rational number or not. We are 99.99999% sure it is irrational. But this is actually an unsolved question. Is -5 pi plus e, or pi plus e, if we want to get even simpler, a rational number or not? We also don't know, for instance, if that's a rational number, pi times e. We know pi is irrational, we know e is irrational. That doesn't necessarily mean their product has to be irrational, though. Open question. you all come up with a proof for that, let me know and I can be famous. Anyways, that was a fun sidebar. Let's look at this set. What is even in this set? Like, how do we describe like individual numbers that would happen to be inside of this set? Anybody give me an example of a number that would be in the set? Truman?
2 plus 1/2.
2 plus 1/2. Okay, so you're plugging in, 2 is a natural number, so if you plug in 2 for n, you'll get 2 plus 1/2 is in this set. I would agree. That would be a number in this set. Luke, can you give me another one?
2.
2. How do you get 2?
1 plus 1 over 1.
You plug in n equals 1. Yeah, so that'll give us 1 plus 1 over 1. It comes out to 2. This comes out to 5 halves. We could have 3 plus 1/3, which comes out to 10 thirds. And et cetera, et cetera. The point is, you get a number in this set by plugging in some natural number for n and finding what's n plus 1 over n. Is this set bounded above? Can we find a single real number that's greater than or equal to every number in this set? Emily, what do you think?
No, because even if you go up to like n equals 1,000, even though your fraction's getting infinitely smaller, it still is smaller.
Yeah, the 1 over n piece keeps getting smaller and smaller, but the n piece keeps going on forever. So 2, 5 halves, 10 thirds gets arbitrarily large. There's no upper bound on how big numbers in that set can be. So we can say no, I'll give this name S. We can say S goes out to positive infinity. Is it bound below though? Can we find any real numbers that are less than or equal to every single element of this set? Truman?
0.
0 is less than 2, 0 is less than 5 halves, 0 is less than 10 thirds. Well, it's less than the first 3 elements. Have you checked the infinitely many other elements in this set to see that 0 is less than or equal to all of them?
No, but it's going to continue increasing because it's a greater and greater n, and it's adding some sort of fraction, so you're never subtracting.
Okay, so meaning if we keep plugging in bigger numbers for n, we're just going to keep getting bigger numbers in the set. So
Yes.
you're never going to get anything smaller in the set than the first number?
Yes.
Yeah, I would agree. Yeah, so we could say yes, for instance, by 0. 0 would be a lower bound for this set. Matthew?
Is that kind of unfair though, because isn't 0 not a natural number? So it's like, would the only example be really 1? Or does it not matter? Because like we're just choosing numbers that are not in the original, like, I guess set. It's
Good question. I would say 1, well, first of all, I would say 1 is not in the set any more than 0 is. Even though 1 is a natural number, but when we consider S,
Right.
we're considering this as a subset of the reals, not as a subset of the natural numbers.
Oh,
So
okay.
any real number could potentially be considered for is it an upper or a lower bound.
But if S was like a subset of like n, then we couldn't be picking numbers that are like 0. or
True.
1.
S also can't be a subset of n because other than 2 here, every single element in S is not going to be a natural number.
Right.
But if we wanted to consider S as like a subset of the rational number, say, then we could not include, say, negative pi as a lower bound, to answer your question. Whereas if we're considering it as a subset of the reals, negative pi would totally be a lower bound. You could also consider numbers like, I don't know, 2 or negative 5 or negative square root of pi over 17 would all be lower bounds for this set.
So sorry, real fast with 2, we used 2 when we plugged in the set, but it's also about like a lower bound.
Huh? Good question. Is 2 less than or equal to every element in this set?
So far, yes.
It's equal to the first element, and Truman's argument says that as you plug in bigger numbers for n, the numbers in the set just keep getting bigger. So I would say 2 is equal to the first element in the set and strictly less than every other one, because these are just going to keep getting bigger in size. So that's why I would say 2 is a lower bound, because it is less than or equal to every element in the set.
Okay.
Or another way to phrase that would be to say there's nothing in this set S that is strictly greater than 2. Or that's strictly less than 2, excuse me.
But what if you started plugging in negative numbers for n?
Then we'd be in a pickle. Can we plug in negative numbers for n with how the set's currently defined?
I'm gonna say the answer's probably no, but I'm not sure.
I would say no, because we're specifying n has to be a natural number.
That makes sense.
If I change the definition of the set, say n could be any integer, which would include like -1, -2, -3, etc., then 2 would no longer work. And in fact, the set would be not bounded below, for similar reasons to why it's not bounded above. Any questions or comments about this? So let's take a look at our bounds here. We'll go back to the set 1 and 10 for a second. If we look at all of our upper bounds, is there an upper bound that's going to be smallest? Emily Rose, what's Cassie?
10.
10 you think is going to be a upper bound that's smaller than all the other upper bounds? Yeah, I would say so. So all of these are going to be upper bounds. In fact, there's infinitely many upper bounds for this set, in the reals at least. But out of all those upper bounds, 10 is going to be the closest you can actually get to having something that's inside of this set without actually being in that set. So in other words, it's sort of the tightest upper bound that you can get on the set. The upper bound that you can get that comes closest to being in the set. Matthew? What if I ask the same question of the lower bounds? Is there a lower bound that's greater than all the other lower bounds? Meaning a lower bound that's closer to being in the set than any other lower bound?
1.
I think so. 1. Out of all of these lower bounds for the set, 1 is going to be the lower bound that is greater than all the others, the closest to actually being in the set. This one's just lower. Emily, if we were looking at the lower bounds, is there a smallest lower bound for this set? Meaning a lower bound that's less than all of the others?
I don't think so.
I don't think so either, because take any huge, humongously negative number, you can always take that number minus 1, and that'll be an even smaller, or an even more negative, let's say, lower bound. So there's no smallest lower bound, and similarly, there's no biggest upper bound for this set. But it turns out we can find a smallest upper bound and a biggest lower bound for the set. Let's look at this set for a second. Can we find a lower bound for this set that is greater than all of the other lower bounds? There's no upper bound, so we can't ask the upper bound question. But out of all the lower bounds for this set, of which there are infinitely many, can we find one that is biggest? Emily Rose?
I guess 2, because it doesn't matter if 2's equal, 2's still a lower bound even though it's equal to one of the values in the set.
Sure. 2 still works as a lower bound. It's also in the set, as Faith asked and I determined earlier, just because something's in the set doesn't mean it can't be a upper or lower bound necessarily. And in fact, 2 is going to be the greatest of all of our lower bounds here. because there's no lower bound for this set that is greater than 2. Even if you try taking something like 2.000001, it's not going to be a lower bound greater than 2, because it's not going to be a lower bound. 2.00, however many zeros I said, 1, is not going to be a lower bound for the set because there's an element in the set that is strictly smaller than it. So 2, out of all the lower bounds, is going to be the greatest. Similarly to how, in this set, 1 is the lower bound that is the greatest out of all of them. Even though 2 is an element of the set in that case, and 1 is not actually an element of the set in that case. It still works as the greatest of all the lower bounds in both cases. Questions, comments, concerns? Groovy. So, we have a special name for the least upper bound and the greatest lower bound. We call it the supremum and the infimum, respectively. So we can actually say, for instance, that B is called the least upper bound, or if you're feeling fancy, call it supremum, for set S, if two things happen. B has to be an upper bound, of S. And we can also say if A is any upper bound for S, B has to be less than or equal to A. It's an upper bound that is less than all of the other upper bounds, in other words. And similarly, we can say L is the greatest lower bound by switching a couple words around. L is called the greatest lower bound / infimum of S if L is a lower bound and if A is any lower bound of S, then L is greater than or equal to A. So in other words, infimum, or greatest lower bound for your set, just means it is a lower bound that happens to be bigger than every other single lower bound for the set. But Ursula, where are you going with this? We're almost there. We need these terms in order to define in order to even see what the third axiom, the spicy one's going to say. So, before we do that though, got an exercise for you all. I want you all to take a couple minutes. If you flip to the next page of the packet, I give you 3 sets, S, T, and J. And what I would like for you to do is for each of those sets, see if you can determine whether or not those sets have upper or lower bounds, and if they do, what's the least upper bound and what is the greatest lower bound.
I dropped the wrong binder.
I'll write them on the board for you.
Thank you.
So go ahead and take a couple minutes, and as always, you're encouraged to work with the people sitting around you, unless you feel like being a social hermit, I guess.
No, I just can't see the board.
Come join us.
Sure.
So you're welcome to join. And we'll come back together in a couple minutes. Just want to give you all a little bit of practice with actually determining for a few sets what's the infimum, what is the supremum.
So,
Is the people upset?
Hi, Sarah. Sorry you're out sick today. You feel better soon. There you go.
So, suppose, I mean, it looks like the lower bound is pi and the upper bound is.
All of these, by the way, are being considered as subsets of the real. So any real number could potentially be
Okay.
least upper bound or greatest lower
The
bound.
thing I find gimmicky with this
that changes things.
is that this is part of this.
Okay.
Is that the same things?
Well,
look to-
if you have
In
a
the
bracket,
example up there.
the supremo would be the number closest to
Two.
a
Two
bracket
more.
or
Element of the
above
set,
it.
so it'd be,
Sure.
But if it's all real
And then,
numbers,
Could 11
given that
be
it's
supreme?
real numbers, maybe root 2 and negative root 2.
Is 11 greater than or equal to everything in the set?
It's gonna be 0 and 2.
I would say it is.
oh, it is?
No,
Yeah.
because x is no.
I would say there's no real number in this set that is greater
So
than,
at least.
that is
the amount is
strictly
going to be like
greater than
negative
11. So 11 is
Negative
greater than or equal to everything in this set.
Okay.
So 11 could still be an upper bound.
Odd 0 2.
Okay.
two. Yeah,
That's kind of correct. I'm wrong. Wait, can we just do this? Oh, wait, no, it is.
yeah. Because it says all x squared less than 2. So the largest x squared that's less than 2 is, well, the equals 2 is root 2.
So B is 1, but L is not.
Well, why?
I mean, like, you put infinite in there, and it'd be 0.
But it's a natural number, so it's gotta be like a positive integer.
Yeah,
N is a positive integer, so L would just be 0, right? I think you're right. Because as you go infinitely large, that fraction goes
Well,
closer and closer to 0.
but B, no, that's not. Oh, shoot. You're right, okay, wait. Is it outputs or inputs? That's set.
The set is the set of the 1 over n,
Okay, wait.
so you get like 1 over 1 and 1 over 2 and 1 over 3.
No, wait, outputs.
Okay,
This
okay,
is,
yeah, I just wanted to make sure you know you're not actually
This is two.
representing it.
No, why?
this is,
If you need me to sign an ad card or anything, happy to do so.
Wait, wait,
yes, and then this is 1. and
Yeah,
this is not
okay.
this. Yeah. It's outputs and inputs.
One
wait,
for an upper bound, for, one is your supremum and you don't have any lower bounds? Or there's at least no, greatest lower bound?
so if it's output, wait,
It's only outputs we're looking at, right?
Yeah,
There's no-
so
yeah,
it-
Correct.
right, okay, so,
Which is why I say any real number could potentially be considered to be a lower bound,
so it can't be.
whether it's a natural number or not.
It can't be less than 0 though, right? The outputs,
which one?
this one? 1 over n can't be less than 0, so.
So like, is it kind of like infinite, where it's like kind of gimmicky with it? Maybe I'm tripped, yeah, it's like converges to that? I see what you're saying.
I mean, it'll never equal 0,
Right, right.
but it'll never be less
But it
than 0
will be an upper
either,
bound.
so.
So it's like the
0
it's the greatest confirmed kill.
Greatest confirmed kill? Never heard it quite described that way.
It's kind of like,
Take another minute or so, then we'll come back together as a
because
class
like,
and
you know,
discuss
if
these.
you put like 1 in here, then like the greatest output would be like plus. And then everything else would just be going out to 0. To the point where like, if you put infinity in here, it's like really close to 0.
I'm still not sure about this one, because if x is 2, then x squared is 4, which is greater than 2. So the outputs, because in this case,
No, but that you're thinking of the inputs. It's like, what is the greatest output cost?
no, but I don't think I am, because the set isn't the set of the outputs in this case, it's the set of the inputs.
Ooh, controversy.
I don't even know how to put it right, but
Oh, I see what you're
it's
saying, where like x is an element of R.
such that x squared is
Yeah,
less
yeah,
than
right,
2.
right, I see that, okay, it's kind of gimmicky with it. So yeah, we're back to the thing.
Because like this, the third one is the set of the outputs, this is the set of the inputs, just the way it's written, it's weird.
Yeah, I see, again, yeah, so if you were just looking at this, I would be right, but if you're looking at this, then with like.
The way,
Yeah,
yeah, because in this case, this is the set of x such that x squared is less than 2. This is the set of 1 over n such that n is an element of the natural numbers.
So let's come back together for a couple minutes and talk about these as a class. So for this set, was anybody able to come up with supremum? Which we can write for short by saying sub of S. You know, sub. Joel? So you're saying 11 is an upper bound for this set that is smaller than every other upper bound?
Yes.
Everyone on board with that? I agree. Of the oomph of S, the infimum of our set, or in other words, the lower bound that is greater than all the other lower bounds, if one happens to exist.
I have
Emma?
a question about the supremum.
Okay.
Why then does it matter whether we have brackets or parentheses, if either way you can include 11?
Oh, predicting my next question. After you did infimum, I was going to ask, what if we change this to not including 11? Would that change your answer? I would say Emily Rose has something to say.
I think it doesn't change what the supremum or the infimum is, it just changes whether or not that number is actually present in the set, which affects like maybe manipulation you're doing within the set, but not the answer for supremum and infimum.
I would agree with that. If we included 11 or pi for that matter in the set, including or not including wouldn't actually change either of these. What it would change is whether the set has a maximum or a minimum element. So in this case, I would say 11 is the maximum element of the set. But if we changed it to not include 11, 11 would still be the supremum. It just would no longer be a maximum element for the set because it's not in the set itself. Does that? Cool. Does the set have an infimum? A greatest lower bound. Luke?
Oh, it is pi, however, it is not included in the set.
Gadzooks. So you're saying pi counts as a lower bound that's greater than all the others, but it's still not in the set, and that's okay, so it can still be an infimum? I would agree. Yeah, so this one, anytime you have an open or a closed or a half open, half closed interval like this, left endpoint, that's your infimum, right endpoint, that's your supremum. How about this one? Set of all real numbers x, that when you square them, you get something strictly less than 2. Sucked. So anybody able to find a supremum for this set, or a least upper bound for the set? Anybody else?
Square root of 2.
Square root of 2? Oh, is square root of 2 going to be greater than everything else in the set? I'd say so. So it's an upper bound. Is it smaller than all the other upper bounds?
Square root of 2 squared is equal to 2, and so therefore it's not in the set, but not greater than it is in the set either.
I see. I would agree. Supremum of the set is going to be root of 2. How about infimum? Or greatest lower bound? Joel?
Negative square root of 2.
Negative square root of 2? Why is that?
Because it's not in the set, but there's nothing that can come closer to the set than square root of negative 2.
So it is a lower bound because it is strictly less than everything in this set, but there's no other lower bound that's going to actually be above it without being in the set or above things in the set somehow. I would agree. Yeah. This set, by the way, this is a fancy way of writing open interval from negative root 2 to positive root 2. So for similar reasons as to why we could say supremum and infimum are these numbers there, we can say the same thing here. And with that, we'll pick things up on Friday. So on Friday we'll talk about we'll start by going through this last example, and then from there we'll go on to talking about our third and final axiom for the reals, the least upper bound axiom, or the completeness axiom. So y'all are prepared at this point to do homework question number 2. encourage you to check that out. And otherwise, I'll see you on Friday.
I finally understand what this is doing, as soon as I saw that, I was like, oh. Or more specifically, the square root of 2. It's probably like, well, that's already not a rational number, so like, of course,
That's gonna
there's
be
no
tough, like
rational
on,
number that
like just
set.
writing on
That's gonna be,
Square root of
versus
2,
paper.
right.
that's gonna be where we're going.
You get used to
We can find the least stuff around for this set in the reals, but if our universe only consisted of rational numbers, this set has the least stuff around. And that is going to be where axiom 3 tells us something different about Q and R.
Yeah, Chris.
Have a good one.
What would you try to